We have considered the mathematical model and the numerical solution strategy. Let's think about quote-unquote hand calculations of expected trends and results. In this case, we also have experimental data. In fact, I chose this particular case study because it has experimental data from NASA. So we'll take a look at what kind of experimental data we have. But before that, let's think about expected results. Here's the airfoil, and we have the flow coming in at an angle. And I'm exaggerating the angle here. And the airfoil is going to deflect the flow down. So it's going to experience a lift. And you're going to get, we expect to see higher pressures on the lower side of the airfoil and lower pressures on the upper side of the airfoil. And as the flow comes in over here, you're going to get a stagnation region over here where you're going to get low velocities. And then as the fluid particle is going around over here, it's going to accelerate, and you're going to get high velocities and low pressures over here. It's called a suction peak. So we expect very low pressures somewhere on the upper side near the nose. The boundary layer, where where there's going to be a lot of shearing from the viscous and the turbulent stresses, is going to be thin at this Reynolds number. When the Reynolds number is high, it means that the viscous forces are small relative to the inertia. And so you have this thin region where the velocity will go from a pretty high value to 0. And we expect the boundary layer to stay attached. That is, we won't expect to see, separation like this when you, the kind that you would get at stall. So we aren't expecting to see any separation. We might get a small separation somewhere near the trailing edge. And from thin airfoil theory, which applies to flow with no viscosity, so thin airfoil theory doesn't consider the effects of viscosity or turbulence, and it applies to thin airfoils, as the name indicates. You can get an estimate of the lift coefficient, which is a non-dimensionalized lift. So the lift is non-dimensionalized in this way. You have the density, you have the square of the free stream velocity, that's the chord length, and that's 1 perpendicular to the screen. So you can think of this as lift per unit span. And that's given by this relationship over here. Alpha is the angle of attack in radians. This is the angle of attack at 0 lift, and this is a symmetric airfoil. So when the airfoil is aligned with the flow, you will not get any lift. The flow will be symmetric over the upper and lower surfaces, so that's 0. And if I use my angle of attack in radians, I get 1.1. So that's kind of the ballpark lift coefficient that I expect. The experimental data is from NASA. You can go to the NASA web page on NACA 0012 airfoil validation. I've given you the link here. You can find it very easily by Googling NASA airfoil validation. It gives you the pressure distribution in non-dimensionalized terms. So Cp is the pressure coefficient, the non-dimensional pressure, versus the non-dimensional x. This is from the Gregory and O'Reilly reference that's given on the NASA web page. And the Ladson paper referred to over there gives you the lift coefficient and the drag coefficient at different angles of attack. And one complication of the experiment is that the flow is not fully turbulent, as we are assuming in our CFD simulation. It's laminar for a little bit over the airfoil, and then it transitions to turbulence. And you can force the flow to become turbulent by tripping the boundary layer, which is done over here. And the way you trip it, can change the results a little bit differently. So the lift is, between 1.07 and 1.08 lift coefficient, depending on how you trip the boundary layer, and the drag coefficient, 3 significant digits, is 0.012, and you can see the drag coefficient is like about 1% of the lift coefficient. It's going to be it's very small, and it's a challenging entity to compute accurately. And the angle of attack is a little bit different from what we have, but those differences are small. So we have lift and drag coefficients from experiments to compare to, as well as the pressure distribution.